Today we'll derive the stiffness matrix for an element that's aligned with the horizontal x-axis in global coordinates. So if we cut this beam element near the ends, we expose internal forces and bending moments. So in our two-dimensional problem, we're going to have displacements in the axial direction at node A and in the lateral direction. And similarly, we have an axial displacement at node B and a lateral displacement. And we also have rotations at node A and B. So each element has 6 degrees of freedom. And axial displacements lead to axial forces developing in the element. So I have the axial force at node A for our element AB and an axial force at the other node. So at node B for element AB. And the lateral displacements and rotations lead to shear forces and bending moments. So we have a shear force at node A and another shear force at node B and a bending moment at node A and a bending moment at node B. And the length of our element is L. So therefore, given the element has 6 degrees of freedom, the stiffness matrix for our element is going to be a 6 by 6. So the columns in the element stiffness matrix correspond to the displacements and rotations. So I have the axial displacement at A, a lateral displacement, and a rotation at A, and an axial displacement at B, a lateral displacement, and a rotation. So note that we drew the displacements and forces in our positive convention. So to the right and up is positive for the forces and counterclockwise for the bending moments. So the forces and bending moments correspond to the rows of our element stiffness matrix. So I have the axial force at A, the shear force at A, and the bending moment at A, and the axial force at B, the shear force at B, and the bending moment at node B. So to derive the first column of our element stiffness matrix, we take our element and apply a unit displacement at node A and fix all the other displacements and rotations. So we have no lateral movement at A and no rotation at A, and NB is fully fixed. So in this case, the element's going to be compressed. So we have the axial force at node A acting in this direction, and the axial force at node B acting in the opposite direction. So in this configuration, our element behaves like a bar element. So it undergoes axial deformation and no bending deformation. So therefore the axial force at A is the axial stiffness by the unit displacement. So that's our first stiffness coefficient that goes in row 1, column 1. And the axial force at B is equal and opposite to the axial force at A. So therefore NBA is minus EA on L. And that's our second stiffness coefficient. And the element does not undergo bending deformation in this configuration, so the other stiffness coefficients are 0. Now if we flip this scenario and apply an axial displacement at node B, with all the other degrees of freedom being 0, then in this column of the element stiffness matrix, the stiffness coefficients will get flipped. So therefore, we get minus EA on L in the first row, and EA on L in the fourth row, and the remaining stiffness coefficients are 0. Now in the second column, we apply a unit lateral displacement in the vertical direction and fix all the other degrees of freedom. So given there's no rotation at A and no displacement and rotation at B, the deformed shape of the beam would look something like this. So it'll be like a double cantilever. And the forces that develop in this beam are the shear force at A and a shear force at B and a bending moment at A and a bending moment at B. So by symmetry, our bending moment diagram looks something like this. So that's equal to MAB at node A and MBA at node B. Noting that by symmetry, MBA is equal to MAB. So the bending moment diagram is plotted on the tension side of the element. And because there's no applied forces in the middle, the bending moment diagram is linear. And now we want to relate the bending moment to the displacement at A. So we use the principle of virtual work. So where we want to find a displacement, we apply a unit load. And if we cut the beam in the middle, by symmetry, the virtual bending moment in the middle is 0, and we have a virtual shear force of 1. So the shear force by the moment arm, which is the length of the element on 2, gives us the virtual moment at node A, which is L on 2. So by symmetry, the virtual moment on the other side is also L on 2. So therefore the displacement at A is the volume enclosed between the real and virtual bending moment diagram. So we have MAB multiplied by L on 2 multiplied by L on 2 on 3 EI. So that gives the volume between these two triangles, and we'll just multiply by 2. So if we turn this equation around, we get MAB is equal to 6 EI on L squared by VA, which is a unit displacement. So that's our first stiffness coefficient corresponding to MAB. So we'll just get rid of these diagrams here and write in our stiffness coefficient. So that would be 6 EI on L squared. And as we said, by symmetry, MBA is equal to MAB. So that gives 6 EI on L squared in the final row. And taking an equilibrium of moments about node B, we get VAB by L is equal to MAB plus MBA. So dividing through by L, the shear force at AB is equal to MAB plus MBA on L. So that would be 12 EI on L cubed. And by equilibrium, the shear force at B is equal and opposite to the shear force at A. So let's write in our stiffness coefficient. So we'll just get rid of this. So as we said, the shear force at A is MAB plus MBA on L. So it'll be 12 EI on L cubed. And the shear forces are equal and opposite. So the shear force at B has a stiffness coefficient of minus 12 EI on L cubed. And now let's get rid of this. So again, if you flip this scenario and instead you applied a unit lateral displacement at node B, so the deformed shape of the beam would look something like this, and the stiffness coefficients of the shear forces will be flipped. So I'll let you do this part as an exercise, and you'll get minus 12 EI on L cubed, 12 EI on L cubed, and the stiffness coefficients corresponding to the bending moments will be minus 6 EI on L squared and minus 6 EI on L squared. And note that in both of these configurations, there's no axial deformation, so the stiffness coefficients corresponding to the axial forces are 0. And this next part is a bit trickier. So in this case, we apply a unit anti-clockwise rotation at node A. So the deformed shape is going to look something like this. So no displacement and rotation at node B, and no displacement at node A. So due to the imposed rotation, we have a bending moment at A, and a bending moment at B, and also shear forces. So if we use superposition, we can superimpose two cases, and in this case, we release the fixity at node A. So what we get is MAB causing a deformed shape that looks something like this. So note that we release the fixity, and MBA causes a deformed shape in the opposite direction. So at node B, we have some rotation, which we'll call theta dash, and in this configuration, this rotation must be equal and opposite to get a fixed support at node B. And now we can apply the unit load method to find the rotation at B. So the real bending moment diagram will be MAB on the left and 0 on the right. So remember that in our superposition, we release the fixity, and applying a virtual moment at node B, we will want to find the rotation. Our virtual bending moment diagram looks something like this, with a magnitude of 1v. So applying the trapezium method, which I'll let you do as an exercise, we get theta dash is equal to MAB by 1 by the length of the beam on 6 EI. And if you do the same thing for our second case, so we have the real bending moment being equal in magnitude to MBA and drops off to 0, and applying a virtual moment at B, our virtual bending moment diagram looks something like this. And the volume between these two triangles is MBA by L on 3 EI. So as we said, the rotations are equal and opposite in both cases to get a net rotation of 0 at this support, so these expressions are equal. And therefore we find that MAB is equal to 2 MBA. So that's our first condition. So in our next case, we want to find the rotation at A, so we apply a unit moment at A. So our virtual bending moment diagram looks something like this. And the volume between these two triangles is equal to the rotation at A for this first case, which is equal to MAB by 1 by L on 3 EI. So that's in case 1. And in case 2, we want to find the rotation at A, so we apply a unit virtual moment at A. So the volume between the real and virtual bending moment diagram in this case is theta A2 is equal to MBA by L on 6 EI. And then superimposing these cases, we get the net rotation at A is equal to theta A1, which is anti-clockwise, minus theta A2, which is clockwise. So we have MAB times L on 3 EI minus MBA, which is MAB on 2. So we have MAB times L on 12 EI. So this is 4 on 12 minus 1 on 12, which is 3 on 12, or MAB times L on 4 EI. So let's just write that here. And if we turn this equation around, our stiffness coefficient is 4EI on L. So let's get rid of this and write in our stiffness coefficient at MAB. And MBA is half of MAB, so let's get rid of this. So the stiffness coefficient is 2EI on L. And as we mentioned, we had shear forces and bending moments in this beam. So if we took moments about node B, for example, we'd have the shear force at A multiplied by the moment arm, being the length of the element, is equal to MAB plus MBA. So therefore the shear force is MAB plus MBA on L. So what we get is 4 plus 2 is 6EI on L on the moment arm. And the shear force at B is equal and opposite to the shear force at A. So let's get rid of this. So what we get is minus 6 EI on L squared. And there's no axial deformations in this case. And if you did the same thing, so instead you apply an anti-clockwise unit rotation at B, so the deformed shape looks something like this. And you can verify that the stiffness coefficients would look something like this. So you'd have the same stiffness coefficients for the shear forces. So we have 6EI on L squared, and corresponding to the shear force at B, minus 6EI on L squared. And the stiffness coefficients corresponding to the bending moments get flipped. So you'd have 2EI on L and 4EI on L. And there's no axial deformation in this configuration. So essentially, we have the element stiffness matrix multiplied by the displacement vector. So we have the axial and lateral displacements and rotation at A, and the axial and lateral displacements and rotation at B is equal to the internal forces of the element. So these are the axial force, shear force, and bending moment at node A, and the axial force, shear force, and bending moment at node B. So we can just remove these here. And this here is our equilibrium equation for our element that behaves like a beam and column, which is known as a beam column element.